Greetings. So welcome to today's class. So let's briefly recap what we studied in the previous class. So we were looking at the analysis of the vehicle response during braking. So if you recall, we essentially discussed this free body diagram of the vehicle during braking, and then like we equated all the forces, and finally got the normal load acting on the front wheel and the rear wheel doing braking, and we interpreted that the normal load acting on the wheels had two components. One was the static load, and another was the dynamic load. Okay, so the dynamic load came in due to the longitudinal load transfer that happens during braking. Okay, so that's where we stop. So today, what we are going to ask is that we are essentially going to ask ourselves the question, how is the total braking force distributed between the front wheel and the rear wheel? Okay, so that is a question we are going to ask ourselves, and we are going to answer in today's class. So let me write down the question. How is the total braking force distributed between the front wheels and the rear wheels? So this naturally leads to an important concept, which is what is called as the brake force distribution. So what is brake force distribution, or BFD in short, is essentially a quantification of how the braking force is distributed between the front and the rear wheel. Okay, so in order to analyze brake force distribution, before we do that, let's define a few terms. Okay, so that we get an understanding. Of course, we will come back to this later on, and then we will see the correlation to other concepts like anti-lock brake systems, in a few lectures from now. But then let me define a few terms. Okay, the first term which I'm going to define is what is called as a longitudinal friction, or some people call it as the traction, or some people call it as the adhesion coefficient, mu. So this mu is different from the mu which was used as a symbol for the brake friction lining coefficient, right? So that's why we use a different symbol subscript there. So this mu is defined as Fx divided by Fz. Okay, so what are these Fx and Fz? Fx essentially denotes the longitudinal traction force. Okay, longitudinal force. It can be the braking force or the traction force. Okay, so this is the longitudinal force. So it can be braking, since we are considering braking maneuvers. It could also be traction. Okay, so when we are essentially driving the vehicle using the powertrain, this Fx denotes the traction force. And Fz is what we have been calling as Wf and Wr. Okay, so only thing is that we are essentially using a different symbol here for Fz. So Fz is the normal load, okay, acting on the wheel. So Fz is the normal load, okay, acting on the other tire road interface. Okay, so why are we studying this, and what is the relationship between what we are studying and these terms? So before doing this, I'm going to introduce one more variable, which is also quite critical in braking analysis. It is what is called as a longitudinal slip ratio. Okay, some people also call it as the wheel slip ratio. Okay, so what is this longitudinal slip ratio or the wheel slip ratio? So the longitudinal slip ratio or the wheel slip ratio, we are going to denote it by the symbol lambda. During braking, is going to be written as Vx minus R omega divided by Vx. Okay, so what are these variables and symbols that come in? So Vx is the longitudinal speed of the vehicle. Okay, so let me write down what it means. Vx is the longitudinal vehicle speed. Okay, so Vx is the longitudinal speed of the vehicle, and R omega is the circumferential speed of the wheel. So if omega is the angular speed of rotation of the wheel and R is the wheel radius, so R omega is the circumferential wheel speed. So during braking, it so turns out that, there is a difference between the longitudinal speed of the vehicle and the circumferential wheel speed. Okay, so they are not equal. So consequently, Vx minus R omega indicates the difference, and it is normalized by Vx, and that gives rise to what is called as a longitudinal slip ratio or the wheel slip ratio. Okay, and this parameter lambda during braking once again varies between 0 and 1. Okay, so what are these two extreme cases? The value of 0 is taken when we have a purely rolling wheel. Okay, when we have a purely rolling motion, Vx becomes equal to R omega and lambda becomes equal to 0. Okay, and when lambda becomes equal to 1, we have what is called as a locked wheel. Okay, so what is this locked wheel? A locked wheel essentially means that, our wheels have stopped rotating, but the vehicle is still in motion. Okay, so what we typically call a skidding, right? So that is what is essentially corresponding to a locked wheel. Okay, so lambda becomes 1 or 100%. Okay, so depending on how we denote that. Now, it so turns out that the longitudinal friction coefficient varies with lambda in this manner. Okay, so let me plot what this variation is. Okay, so if we look at the variation in mu versus lambda, sorry. So what happens is that, like, initially there is an increase with lambda, and then like there is a peak beyond which the value of mu keeps going down, and then like it enters what is called as an unstable region, and then like it progressively keeps on decreasing till the wheel has gone to a locked state. Okay, and this value of mu, okay, which is the maximum value, is what is called as a peak value of mu, denoted by mu p. And let's say we indicate that the value of lambda at which the peak value happens is denoted by lambda p. Okay, so the value of lambda at which we get the peak friction coefficient is what like most closed loop wheel slip regulation systems will try to regulate the wheel condition around. Okay, so that like we essentially have the maximum possible braking force, right, and consequently the maximum possible uh, deceleration and the least possible stopping distance, right? So this is the typical mu lambda curve. We will also look at a few more aspects related to the mu lambda curve and some more physics associated with when we discuss anti-lock brake systems shortly. But then right now, let's take this curve and then let's essentially take our analysis forward. Okay, so some people will call it as the mu lambda curve, okay, for obvious reasons. Okay, so this relates the value of mu with lambda. Okay, so that's what we have here. Now we can see that mu p is what is mu p? Mu p is the peak value, right, of the longitudinal friction coefficient or the longitudinal traction coefficient. Okay, so mu p is the maximum or peak longitudinal tire road friction slash traction slash adhesion coefficient. Okay, so from here onwards, just for convenience, we will just use the term friction coefficient. Okay, so that's the most commonly used term for this, but these are all alternatives which are used. Okay, so friction / traction / artificial coefficient. Okay, so it so turns out that when we go to the right side of the peak, right, to high slip regions, we are going to get into what is called as unstable region. Okay, so we'll see why this is called unstable. What is the impact on vehicle performance and so on. So typically, when we talk about wheel slip regulation, we want to regulate the wheel slip around the peak mu regions. Okay, so that we remain in stable regions of operation. Okay, so we'll study more about this as we go along. Another big challenge here, which we will realize when we also talk about it in ABS, is that the knowledge of this mu p and particularly this lambda p, right, is tied up to the condition of the tire rod interface. Okay, so it's going to vary depending on the state of the tire rod interface, and that also poses some additional challenges, right? So in their estimation and control. So we will discuss that also later. All right. So now coming back to our discussion. So where did all this discussion start? We asked ourselves the question, how is the total braking force distributed between the front and the rear wheels? Okay, so we have been doing some braking analysis where we got expressions for WF and WR, which included static loading plus dynamic loading due to longitudinal load transfer, right? So that's where we are. Now let's combine all these things, right? So mu p is going to be equal to fx max, right? Because mu p indicates the maximum value of this friction coefficient divided by fz. Okay, so this implies that the maximum longitudinal friction or traction force, okay, friction or traction force is essentially denoted by fx max. That's going to be equal to mu p times fz, and fz is what we have been calling as w, right? Wf or wr, right? So we have been calling it as w. I just wrote it in a general term. Okay, that's the normal word. So now coming back to our analysis, right? So we are just going to use these concepts and get some expressions. So coming back to our braking analysis, since we have got expressions for WF and WR, the maximum braking force from the vehicle's perspective, right? So available at the tire rod, at the front tire rod interface, right? So the front tires is going to be equal to, let's call it as FBF max. Okay, F subscript B indicates braking force, another subscript F indicates the front tires, comma max indicates the maximum value, right? So that's going to be equal to mu P times WF, and that's going to be equal to mu P times, if we go back, let's look at the expression for WF, right? So we got an expression for WF in this manner, right? So you recall from equation number 2, WF was WL2 by L plus H by L times FB plus FRW. Okay, so that's what we are going to substitute. So let's substitute that here. So we are going to get mu P times WL2 by L plus H by L multiplied by, of course, FB plus FRW. Now we are considering the case where we are looking at the maximum brake force. So we will just substitute FB max instead of FB. Okay, so I hope it is clear why we are doing this, right? So because we are considering the case where we are looking at the maximum braking force available. Okay, so that's why we are making this change. Now, this FB max, what is this FB max? So obviously this FB max is going to be equal to FBF max, okay, plus FBR max. So what is this FBF max and FBR max? They are going to be the maximum braking force at the front and the rear wheels, right? So that one can write it as mu p times WF, because FBF max is mu p times W. FBR max is going to be mu p times WR, right? So I'm sure these expressions are clear to us. So this will give us mu p times WF plus WR, okay? And that's going to be equal to mu p times W, okay? So I hope it is clear how we got mu p times W as the formula for FB max, okay? So that is the maximum braking force available on a surface with a peak friction coefficient of mu p and a vehicle weighing a weight of W. Okay, so that's how we should interpret this formula. Okay. Now, having obtained what this is, so we go back and simplify this expression. So FBF max is going to be equal to mu P W L2 by L plus H by L times mu P times W, that's FB max, plus FRW. Okay, so that's what we have. So consequently, this FBF max, one can write it as mu P W by L times L2 plus H times mu P plus FR. So what have we done? We just have taken W by L as common, right? And then like we have got this expression. Okay, so this is the expression for the maximum braking force available at the front tires. Okay, so I hope it is clear. So let us similarly derive the maximum braking force available at the rear tires. So similarly, a similar process followed. Okay, so the maximum braking force available at the rear tires is the following. Okay, so what is that? That's going to be equal to FBR max. That's going to be equal to mu P times WR. And we have already derived the equation for WR, right? What was the equation for WR? If we go up, okay, so we look at this equation number 3, right? WL1 by L minus H by L FB plus FRW, right? So we go there. We are going to use that one. So WL1 by L minus write this subscript one very clearly, WL1 by L minus H by L. Of course, we should write FB max here plus FRW. Okay, so just substituting for FB max as mu P times W and simplifying it will immediately give us FBR max, similar to what we got previously for the front wheels. For the rear wheels, it's going to be mu P W by L times L1 minus H times mu P plus FR. Okay, so I hope it's clear how we got this, right? So very straightforward. Okay, so how we get the expression for the maximum brake force available at the rear wheels. Once again, on a surface with a peak friction coefficient of mu P. Okay, so now we have got the equation for FBF max, and then we have got the equation for FBR max. So we just divide the two expressions. Okay, so FBF max divided by FBR max, okay, is going to be equal to L2. So mu P by W will get cancelled on the right hand side, right? So we are going to get L in the numerator, we are going to get L2 plus H times mu P plus FR divided by L1 minus H times mu P plus FR. Okay, so this this ratio is what is called as the ideal brake force distribution. So what have we got here? We have got the ratio of the maximum brake force available at the front wheels to the maximum brake force available at the rear wheels, right? And this is what is called as the ideal brake force distribution. So why is it called ideal brake force distribution? Because you will get the best possible braking, right? When we are having the maximum brake force at the front wheels and the rear wheels, right? Which are essentially FBF max and FBR max. And if that is the case, we will get the maximum brake force total, and that will result in the maximum deceleration and the smallest possible uh, stopping distance, right? So that is why this is called as the ideal brake force distribution. Brake force distribution is abbreviated as BFD, okay? And typically what happens is that like we essentially use some terminology, like this ratio is taken to be a ratio of two factors less than one, typically called as KBF and KBR. KBF denoting the fraction of braking on the front wheels, KBR denoting the fraction of what to say, braking on the rear wheels. Okay, so let me not write it this way. Sorry about that. Okay, so if let me write it very carefully. Let's say KBF, what to say, is the fraction of braking on the front wheels. Okay, so that means that KBF is typically written as FBF divided by FB. Okay, so it is the braking force from the front wheels to the total braking force. Okay, similarly, KBR is going to be the fraction of the braking force from the rear wheels. Okay, so similar to this. So this is going to be the fraction of braking available on the rear wheels. Okay, so that is KBR. So KBR is going to be equal to FBR divided by FB. Okay, so that is the fraction available on the front wheels. And typically what one immediate thing which we can essentially see is that KBF plus KBR becomes equal to 1. Okay, so because if we add the two, we are going to get 1, right? Is it not? Because KBF is the fraction of the total braking force on the front wheels. KBR is the total braking force on the rear wheels. So we add the two, we are going to get the total to be 1. Okay. So for example, right? So let's say, like we have a 70-30 brake force distribution, right? So let's say BFT of, let's say 70 is to 30, right? Front is to rear. Okay, so then what it means is that like KBF is going to be equal to 0.7 and KBR is going to be equal to 0.3. Okay, so that is the implication, okay, of braking force being 70-30 or 70%, 30%. Okay, so when people use percentage also, they will say 70%, 30% and so on, right? So one can essentially interpret that way also. Okay, like so as an example, we are considering brake force distribution of 70-30. Okay, so this is a convention or a symbol that we need to know. All right. So if we go back here, this ratio is going to be the ideal brake force distribution. So let me write this with now that we know what KBF and KBR are. Okay, so what we have obtained through this formula, through this derivation, is the ideal brake force distribution. Why am I calling it as ideal brake force distribution? Because that is the maximum what to say, distribution, it is or the maximum brake force that one can get, right, for the vehicle and the situation under steady. Okay, so that is why it's called as the ideal brake force distribution. And then we put a subscript, another subscript I to it. Okay, like just to indicate that this KBF and KBR, what we have derived in this formula, corresponds to the ideal condition. All right, so that's how we should. So this is the expression for the ideal brake force distribution. So we can immediately observe something which is interesting, right? So the ideal brake force distribution, sorry, ideal BFT, okay, it depends on mu p. Okay, so it depends on the maximum friction coefficient at the tire road interface. Okay, so that's one thing, right? So because if you look at the formula, we have mu p there. Although rolling resistance comes into play, relatively the value is smaller. And the other important factor on which it depends on, it is the CG location. So we can see that L1, L2, and H play an important role in determining what is the ideal brake force distribution. Okay, so this creates a lot of interesting scenarios and challenges, right? Why? Because point number one, okay, if we have, let's say, a dry road surface as against a wet road surface or a snowy road surface, right? And an icy road surface, this brake force distribution is going to vary, right? So depending on the type of the road surface that we are going to get, we are going to have a different value of ideal BFT, right? And if we have a laden vehicle, a partially laden vehicle, okay, and a fully unladen vehicle, right? So obviously the values of L1, L2, H will change, and that's also going to change the ideal brake force distribution. Okay, so this creates an interesting perspective also on why we need active devices like ABS, right? So because let's think about it. Let's say, like we have a passenger car, right? So it is designed for some load rating, right? And under some road conditions. And let us say it is supposed to operate on a dry road with a peak friction coefficient of, let's say, 0.9. Okay. Now, like it rains and then like the peak friction coefficient reduces. Okay. And then the brake force distribution between the front and the rear will change. Now, during the vehicle's operation, we can't just go and change the brake system, right? The friction brake system is what it is. We have designed it and sized it for the best operating conditions, which we think we will encounter in practice. And then we would have done the manufacturing and assembly, right? But however, now when suddenly the road conditions change, right? So the ideal brake force distribution changes, then what do we do about it, right? So that's one interesting perspective that comes about from the dependence of the ideal BFT on mu p. Okay, that's point number one. Now the second point. Okay, so let me take another example. Let's say we have a standard single unit truck. Okay, let's say that weighs around 16 ton. All right. So the brake force distribution has been designed for that, right? So now let us say that a truck is loading some cement and then it goes to its destination, delivers the cement, and now it's completely empty. Okay, its mass, let's say, goes to 4 ton. So now there's a huge difference, right, between the laden and the unladen vehicle mass. And this also affects the mass distribution between the front wheels and the rear wheels, and consequently will affect the values of L1, L2H. So although the same vehicle may operate on the same surface, right, its loading conditions can also differ drastically. And that can in turn influence the ideal brake force distribution, right? So these are important aspects for us to consider, right? So, and then like these may in turn influence how we have to, what to say, operate the brake system, and why, we need active safety systems that regulate these brakes, right? To avoid what is called wheel lockup. Because if we go and apply too much brake, then what can be sustained at the tire road interface for a particular operating condition? We have locking of wheels. Okay, so and that is something which should be avoided. All right, so that's in that context, we will look at ABS shortly. But before we go to wheel lockup, any questions on what we have learned till now? Okay. So, yes, please.
Sir, these conditions hold good when there is a constant velocity, right, sir?
So, which conditions?
The ideal brake force distribution, the equations which we arrived here, right, sir? These are all for the vehicle going at a constant velocity, right? Which means there is
No,
no acceleration.
no. So this is a dynamic thing, right? So please note, like, see, the constant acceleration velocity was for cornering. See here, if you go back to the free body diagram, which was the starting point of a discussion, we are braking, and this acceleration is a time varying quantity. So since the acceleration is non-zero, obviously the vehicle speed is changing, right? Is it not? Okay.
Okay, sir.
Okay, so yeah. So please note that scenario. Okay, so here vehicle speed is changing. Okay, we are braking the vehicle. Okay, any other questions before we go to a simple analysis of wheel lockup? No. All right. So what we are essentially going to ask ourselves in this discussion is that, like, can we get simple expressions on which provide us bounds on the vehicle deceleration, at which, like, let's say front wheels or the rear wheels will lock. Okay, and when will a wheel lock? Because the wheel will lock when we are essentially trying to get more uh, force output, braking force output from a wheel than what the tire road interface can sustain. Okay, so let's look at it in some more detail. Okay, so let us consider, for this particular analysis, let us consider only the inertia and the braking forces. So we consequently let us neglect aerodynamic drag, grade resistance, and drawbar pull. Okay, so this is a reasonable assumption to make. So these numbers are going to be typically smaller when compared to the magnitude of the brake force, particularly at the peak levels. So we essentially neglect all these other loads, and we will consider only the aerodynamic drag. We consider only the braking force. Okay. So in fact, some people will also neglect the rolling resistance. Okay. So that is also small. Okay. But let's keep rolling resistance for the time being. Okay. So then the governing equation of motion will just become ma equals the net force, which will be equal to nothing but fb plus frw. Okay, so this is the governing equation. What happened to other forces? The aerodynamic drag, the grade resistance, drawbar pull are all neglected. So if we go back to this free body diagram and the equation that we wrote down in the previous class, we recall this equation, right? So RA, RD, W sine theta is everything is neglected in equation 1. So that is why we get W by GA to be equal to FB plus FRW. Okay, so that's what we have written now. Okay, so that is the equation. And one can easily derive the equations for WF and WR as the following. I leave this to you as exercise for you to do. You don't need to submit it, but please repeat the same exercise, and you will see that this becomes W by L, L2 plus A by G times H. Pretty straightforward, because it was FB plus FRW times H. So FB plus FRW is W by GA, right? So that's why we get this expression. Okay. Nothing very difficult, very straightforward. And WR is going to be W by L, L1 minus A by G H. Okay, so these are the expressions for WF and WR. Okay, so now we are given a brake force distribution of KBF is to KBR. Okay, so suppose someone tells us that, okay, the brake force distribution is 60-40. That means that KBF is 0.6, KBR is 0.4. Okay, now the question that we are going to ask ourselves is the following. Under what conditions would the front or the rear wheels lock? Okay, so that is the question we are going to ask ourselves. Okay, under what conditions will the front or the rear wheels lock? Okay, now let's go back. Okay, so if we are given a brake force distribution, right? So FBF will become equal to KBF times FB. How do we get this? Because we are given a brake force distribution of KBF and KBR. Total braking force is FB. So what is there on the front brakes? It's going to be KBF times FB. And this can be written as KBF times FB. FB is going to be equal to W by GA minus FRW. Okay, so that's what we get. How did we get that? We got it from this equation, right? So we can eventually see that FB is equal to W by GA minus FRW. Okay, so that's what we got. And this will become, if I take W out, this will become KBFW times A by G minus FR. Okay, so now when would the front wheels lock? So the front wheels would tend to lock. Okay, so they won't immediately lock. The front wheels would tend to lock when the brake force that we are asking is going to be greater than the capacity at the tire road interface, right? So FBF is the brake force that we are asking is going to be greater than the peak friction coefficient mu P times WF. Okay, oops, something happened. 1 minute, I think. Let me restart screen broadcasting. 1 minute. Okay, yeah, I think, yeah, now I think it's back up. So sorry about that. So when the essentially the front wheels would tend to lock when the brake force that we are asking from it is greater than the capacity at the tire road interface, right? Which is mu P times WF. So we are going to look at the limiting condition. So in the limiting condition, what happens? The limiting condition of the tire road interface, we have FBF to be equal to mu P times WF. Okay, so this is the limiting condition. Why am I calling it as a limiting condition? Because beyond this, if we increase FBF, the front wheels will tend to lock, right? And what is this mu P times WF? This mu P times WF is indicative of the maximum longitudinal friction force at the front tire road interface, right? So that's something which we already looked at. Okay, so this is the maximum longitudinal friction force at the front tire road interface. So now what we are going to do is that we are just going to substitute things and then evaluate. Okay, so let's do some, we will do some algebra here. So please note that FBF is equal to mu P times WF. What is FBF? We get from this equation. Okay. So FBF is going to be equal to KBF W times A by G minus FR. Okay, so that is FBF, and that's going to be equal to mu P times WF. What is WF? WF we have here, right? That's going to be W by L, L2 plus A by G H, right? So I'm just going to write it there. So that's going to be W by L, L2 plus A by G times H. Okay. So if we simplify this, W and W get cancelled off on both sides. Okay. And then like we can just simplify things. So what we are going to get is KBF, I bring L to the other side. So I will get KBF L A by G minus KBF FR times L. That's going to be equal to mu P L2 plus mu PH times A by G. So we can see that we have this factor A by G common on both sides. What is A by G? A by G is the normalized longitudinal deceleration, right? So A is the longitudinal deceleration, G is the acceleration due to gravity. And as we discussed, typically in vehicle dynamics, we normalize all the decelerations with respect to acceleration due to gravity. Okay, so that's why we are writing as A by G. And what happens is that, like, if we collect the terms, we are going to have KBF times L minus mu P times H multiplying A by G. Okay, and that's going to be equal to mu P L2 plus KBF FR L. Okay, so if we cross multiply, we are going to get A by G is going to be equal to the following. KBF, 1 minute. Mu P L2 will be the dominating term. So let me write it that way. So mu P L2 plus KBF FRL divided by KBFL minus mu PH. Okay, so this is an important expression. So what does this expression tell us? So this expression gives us a formula to calculate what will be the peak vehicle deceleration beyond which the front wheels will tend to lock. Okay, so consequently, we will put a subscript F here, okay, in this formula, and we call it as A by G subscript F, okay, and that is this formula. So what does this indicate physically? It indicates what is the vehicle deceleration at which the front wheels tend to lock up. Okay, if the vehicle deceleration increases any further, like the front wheels would surely lock, right? So this is the limiting deceleration, right, at which the front wheels would tend to lock up. Okay, so that is the expression for A by G subscript F. So one can essentially derive a similar expression for A by G subscript R. That I leave it to you as an exercise. We will complete that exercise in tomorrow's class, and then like we will also like interpret a few more aspects related to braking performance before we go to anti-lock brake systems and the corresponding concepts. Okay, but I hope it is clear how we got this expression, right? So we wanted to essentially get what is the peak deceleration at which the front wheels will tend to lock up. Okay, so please derive a similar expression for A by G subscript R, which is the peak weight deceleration at which the rear wheels would tend to lock up. Okay, please follow a similar process to get a corresponding expression. All right. Okay. So I think this is a good place for us to stop in today's class. Are there any questions based on what we have discussed today?
Sir, when L1 and L2 H becomes a variable, like based on shifting of the weight from front to rear or something. So will it be like some other studies we need to do, or it will be the same?
So when L1, L2, and H vary, what is going to happen is that the brake force distribution will vary, and also as one would observe, this value of A by GF also varies, right? So for example, let us say A by GF comes as 0.6, just as an example, right? So what does that physically mean? When the vehicle deceleration is 0.6 times G, the front wheels will tend to lock up. Now, due to some reason, the center of gravity has shifted, okay, and A by GF has become 0.5. What does it mean in the new scheme of things? For the same brake force distribution that you and I are using, now at 0.5 G itself, the front wheels will tend to lock up, and that's something which is not desirable, right? So then the question becomes, like how do we take that into account, right? So those are all interesting problems to ponder. Okay, so that's where like we get into what is called active brake control and so on, right? So we will see some interesting concepts, particularly associated with ABS. Okay, so and there are many other active brake system controllers that can be developed. Okay, based on these concepts.
Okay, yeah, sure, sir. Thank you.
Yeah, welcome. Okay, any other questions?
Sir, how do we find out this graph of mu versus lambda?
Okay, good question. So this is a very useful graph for explaining the concept. Okay, so but in real life, how do we get this, right? And as I mentioned, not only is this mu lambda curve dependent on the type of road surface, okay, it is also dependent on other things, okay, which we will anyway discuss in next class or in a couple of classes. And then I will pose the problem as a controls problem, and we will see how one could essentially try to figure not the mu lambda curve, but then we want to figure out what will be lambda p. Okay, so that is what we will be interested in. Okay, so we'll discuss those things. Okay, please give me one class or a couple of classes, then we'll come back to the same question. All right, so to answer to the point, like in real-time operation, you and I don't know what the exact mu lambda curve is, right? So then how do we design active brake controllers? That's something which we'll study. Okay.
Okay, sir.
Yeah. All right. Any other questions? Okay. So if not, let me stop recording. Thank you.